Good day. I'm Engineer Mark, and today I'll be talking about how artificial intelligence is reshaping one of the world's oldest professions, farming. My topic is next generation farming, AI driven technologies and trends in smart agriculture. With the global population expected to reach nearly 10 billion by 2050, traditional farming methods simply won't suffice. We're facing climate change, water scarcity, and rising costs. This is where smart agriculture comes in, combining AI, IoT, and robotics to help farmers make better decisions, increase yields, and minimize environmental impact. Now let's have an overview of our lesson today. First, AI-driven edge computing. Number 2, computer vision in crop or livestock monitoring. For the third one, we have AI for irrigation and research optimization. 4, agricultural robots and drones. And then lastly, we have IoT, AI platforms for precision farming. So let's start our discussion. Let's begin with edge computing. Unlike traditional systems that send data to the cloud, edge devices processes information locally, right on the sensor or microcontroller. This allows real-time decisions even in remote areas. For example, a pest detection sensor can classify leaf diseases on the spot without needing an internet connection. Edge computing is a computing paradigm where data is processed directly or at near source of data generation, such as on sensors, IoT devices, or microcontrollers. Instead of sending it to distant cloud or centralized data center. When paired with artificial intelligence, edge computing enables local AI models to analyze data in real time without relying on constant internet connectivity. So what is AI-driven edge computing? So it involves running lightweight AI models directly on edge devices like Raspberry Pi, NVIDIA Jetson Nano, Arduino with TinyML, smartphones, or embedded AI chips. The AI analyzes sensor data locally, minimizing the need to transmit large datasets to the cloud. And what are the benefits? So, real-time processing, so immediate insights and responses. Example, we have detecting a pest instantly on a leaf. Also, it reduces latency. No need to wait for the cloud round trips, so critical for time-sensitive decisions like stopping disease spread. Offline functionality works in rural or remote farms with poor internet connectivity. Moreover, we have data privacy. Sensitive data stays on site, improving security and ownership. Here's a simple application. An Edge AI module in a tomato field scans leaves using a camera, detects early signs of blight, and alerts the farmer instantly. This is not only saves time but can prevent large-scale crop damage. A smartphone AI-powered sensor uses a built-in camera and trains CNN convolutional neural network to scan leaves. The devices classify leaf images on device to detect symptoms like blight or mosaic virus. If this is detected, the farmer receives immediate alerts or recommends actions. No internet required, all processing is done on the field. Here we have an example of a real-world tools, Plant Village Neuro. It is developed by Penn State and FAO. It uses AI on mobile phones for diagnosing plant diseases. On the other hand, we have Leaf AI. It utilizes TensorFlow Lite, a machine learning framework to run deep learning models on devices like Raspberry Pi and ESP32 microcontrollers. This allows for edge-based inference, enabling AI applications to function directly on the device without needing a cloud connection. TensorFlow Lite is designed for resources-constrained devices, making it suitable for edge, AI, and IoT applications. Next is computer vision. Using cameras and AI algorithms, farmers can monitor crop health, detect pests or weeds, and analyze livestock behavior. For example, CNN-based models can identify disease in maize leaves or monitor cow activity to detect early signs of illness. CV. So, computer vision is a field of artificial intelligence that enables machine to see and interpret visual information, such as images or video. In smart agriculture, CV helps automate the monitoring of crops and animals using cameras and AI algorithms. This allows for early detection of problems, reducing manual labor and improving productivity. Some applications of agriculture in crop monitoring, first is disease detection. AI models detect symptoms like spots, wilting, or discoloration of leaves. For weed identification, CV systems distinguish between crops and weeds for targeted weeding. Growth tracking. Drones or fixed cameras monitor plant size, density, and color to assess health. Fruit counting and ripeness. Vision models count fruits, for example, apple, tomatoes, and estimate ripeness based on color and texture. Benefits: we have automation, reduces labor-intensive inspection, precision, early and accurate detection of issues, improves yields and reduces costs. Animal welfare. Continuous monitoring improves the health management of livestock. Data logging. Visual data can be archived for trend analysis and decision making. One example of CV is Blue River Technology. Blue River Tech is bringing machine learning to the field. Blue River Technology is a California-based machinery enterprise which is focusing on designing, producing, and selling computer vision-based robotics that can be used to help agriculture industry, specifically in cotton weeding. In addition, farm spraying algorithms can distinguish plants, excluding empty soil for spraying range, and even label specific parameters of a weed like its sort or canopy stage. The company has created a machine called See and Spray. The machine uses computer vision and artificial intelligence to detect and identify and also make management decisions about individual plants in the farmer's field so that the plants that are essential to the farmers and consumers are not unintentionally destroyed by the herbicide. The machine has robotic nozzles to ensure accurate spraying of herbicides. Furthermore, the machine sprays only the necessary weeds with herbicides in an attempt to curb weeds that are resistant to herbicides, as these are growing in number and could eventually greatly hinder farmers' produce and production capabilities. This See and Spray technology can distinguish between wanted crops and unwanted pests to apply only pesticide where it is needed the most, saving farmers money, improving yields, and helping the environment all the same time. For the livestock monitoring, we have Connectera, a wearable plus CV platform that detects cow behavior changes.
Certainty, things can change within a day. You just have to be really focused and keep track of it all. The cow's health is of the utmost importance. A sick cow is not producing milk and she will also require more attention. That's why we adopt the technology. We're searching for things that can help us out. And artificial intelligence can be a great tool to give farmers more insight. The app of IDA helps me to keep track of my cows, so it makes life easier.
IDA is really the dairy farmer's assistant. It starts by a sensor that sits on the neck of a cow. And by analyzing the movement of this sensor, we use TensorFlow and machine learning to figure out what the cow is doing. And we can actually distinguish multiple behaviors of this cow: eating, ruminating, drinking, standing, laying, and walking. So if IDA sees a certain pattern in the behavior, IDA can actually figure out the disease that the cow is prone to get, and she can warn the farmer to take care of her.
The key thing with IDA is that it learns. Using TensorFlow, an open source tool that Google has authored, it learns the behavior of animals and it gets better over time.
That helps me to improve the efficiency of my milk production and also improve animal welfare to keep the cows healthy and comfortable.
We see farming as evolving. Technology and the farmer are going to work together.
About 1 billion people globally are engaged in dairy farming. And by solving some of these problems, we're able to help farmers run a more efficient farm.
And we can do it in a way that is sustainable for us.
Additional in CV is Taranis and Pix4D. Taranis partners with a large network of drone service providers, DSPs, who capture imagery of customers' fields. Ideal time windows to arrive at growers' fields are determined by analyzing crop growth models based on individual planting dates and regional weather patterns. Pilots are directed to capture the leaf level imagery, and then they promptly upload the images to the company's servers for processing. Direct management of pilots' schedule and their arrival of growers' fields during the relevant crop growth stages allow for the collection of the rich, large and diverse datasets necessary to train the AI models. Pix4D, both of them are drone-based imagery for identifying pest zones and estimating yield. AI-based irrigation and resource optimization systems use artificial intelligence algorithms to analyze environmental and crop data to automate irrigation schedules, minimize water, fertilizer, and energy use, optimize crop yield and resource allocation. These systems rely on inputs like weather forecast, soil moisture, plant health, and historical data to make data-driven decisions. How it works. As you can see, we have sensors. So the sensor inputs collect real-time data on soil moisture, temperature and humidity, rainfall and sunlight. And then, for the AI analysis, it predicts and when and how much to irrigate using machine learning models. It also estimates evapotranspiration, EP, and crop water demand. Last, we have the control system. It activates drip or sprinkler systems accordingly, optimizes use of fertilizers or nutrients if integrated with fertigation. A study entitled Artificial Intelligence to Optimize Water Consumption in Agriculture, a predicted algorithm-based irrigation management system. They have an experimental tomato crop that has been tested throughout the 2023 summer season in a living lab located in Parma, northern Italy. The Living Lab was developed by the University of Parma in collaboration with Azienda Experimentale Steward with the framework of the National Research Center for Agricultural Technologies. Specifically, the Solanum lycopodium LCV Heinz 1301 was grown according to the organic guidelines and specific instructions given by the involved research teams to carry out various experimental activities on different issues. In this perspective, a set of parameters were continuously monitored throughout the experimental season by a 3-layer LoRaWAN network-based framework. Specifically, it provides irrigation recommendation based on a 3-day weather forecast and data collected from the device installed in the Living Lab. As you can see in the figure, it shows how the proposed system was characterized by the acquisition layer, which enable real-time data monitoring and data collection into a network server. And then, The intermediate layer allows the data to be processed and stored in a cloud where they can use by the user application or processing nodes. We also have the data of the soil moisture properties derived from the data acquisition layer. Here is the example of the AI-based irrigation and resource optimization. In a typical setup, soil moisture sensors send data to an edge device. The AI model evaluates conditions and decides whether to open or close irrigation valves. It's autonomous, adaptive, and extremely efficient. Example of system, we have Arable Mark and Arable Pulse. AI plus IoT monitoring microclimate, crop stress, and guiding irrigation. CropX that combines soil sensor data and machine learning to offer tailored irrigation device. NetBeat by Netafil. We have cloud-based AI irrigation for real-time optimization. Then lastly, the Microsoft FarmBeats. It integrates AI, sensors, and weather data to improve irrigation schedule. Let's talk about automation. Robots are now capable of planting, weeding, and harvesting with a minimal human input. Drones, meanwhile, are used for aerial imaging, crop spraying, and health assessment. AI enables them to operate intelligently, identifying exactly where intervention is needed. The first one here is eco-robotics. It is an ultra-high precision spraying technology that performs weeding operation in grassland and row crops. Using cutting-edge AI, its vision and computer systems detect and selectively spray the weeds with microdose of herbicide. Next, FF Robotics is a developing robotic fruit harvester for the commercial market. The company's robotic system uses computer vision to identify ripe fruit and emulates the motion of a human hand while picking apples. According to the company's website, the robotic harvester is 10 times faster than human pickers. Although still in development, the company has received funding from European Union's Horizon Research Program. Last, the Astronaut A5, Lely's latest milking robot. It uses a laser-guided robot arm to clean the cow's udder before attaching teeth cups one at a time. Subsequently, we also have agricultural drones. They are used for aerial imaging and mapping. They capture multispectral and thermal images for plant health monitoring and DVI analysis. They also detect disease, pest, hotspots, or nutrient deficiency. Moreover, for precision spraying drones, they apply fertilizers or pesticides only where needed using AI-generated prescription maps. We have an example here, the DJI Agras T50.
Ready, steady, go. Meet the brand new DJI Agras T50. Ag drone spraying demands extreme efficiency to protect crops from diseases, pests, and weeds. The DJI Agras T50 has a 40 kilogram spraying payload and can cover up to 21 hectares per hour. Equipped with a dual atomizing spraying system, it produces fine, uniform spray droplets. The flow rate is increased by 33% to 16 liters per minute. For large volume operations such as fields and orchards. For orchards and forestry spraying, DJI Agras T50 can be upgraded with a pair of centrifugal sprinklers, increasing flow rate up to 24 liters per minute, extending coverage to the tops and bottoms of leaves. DJI Agras T50's brand new solenoid valves completely eliminate drips and leaks. Spreading fertilizer over large areas requires elite power. The DJI Agras T50 has a 50 kilogram spreading payload and a flow rate of up to 108 kilograms per minute. We've doubled the spreader motor's torque and designed a new spiral channel spinning disc to spread material more uniformly. You can also switch to smaller hopper gates for lower flow rate spreading with higher precision. When facing complex environments, the DJI Agris T50's active phased array radar, with double the number of RF channels, grants higher detection precision. Together with its rear phased array radar, DJI Agris T50 can achieve multi-directional obstacle sensing. With 2 sets of binocular vision sensors, it can accurately sense terrain and depict obstacles in detail for automatic obstacle bypassing and terrain following over steep slopes. The radar system works with a high-resolution FPV gimbal camera and can conduct aerial surveys of slopes up to 20 degrees to meet most orchard operation needs. With DJI RC Plus and its real-time mapping capabilities, automatically identify fruit trees and obstacles to generate accurate, fully automatic 3D flight routes. The 4-antenna O3 transmission system offers stable and reliable connectivity, even when working with tall crops. When flying in areas with hills and obstacles, the optional DJI Relay module helps maintain connectivity for improved operational safety. With the DJI Mavic 3M, capture high-resolution maps of fields and orchards to elevate DJI Agris T50's work efficiency. For fields with growth variations, generate prescription maps to guide DJI Agris T50 in variable rate spreading and spraying to grow more with less. Minimize downtime with fast, continuous charging powered by the D12000 IEP multifunctional inverter generator. Its electronic fuel injection technology improves fuel economy. DB1560 intelligent flight batteries have air-cooled heatsink, allowing for 9-minute fast charging. The C10000 intelligent charger can charge batteries directly with utility power. Stable, reliable, smart. This is the new generation of DJI Agris drones.
For the livestock monitoring, they track animal movements over large areas with thermal cameras and GPS. When AI and IoT work together, the entire farm becomes connected. Sensor collect real-time data and AI models analyze it on central dashboards. Farmers receive alerts and recommendation via mobile apps. It is like having a smart assistant for every hectare of your land. The core concepts, the Internet of Things, network or of smart devices, example, soil sensors, weather stations, drones that collect real-time data. The artificial intelligence, AI, processes the data using models like machine learning and neural networks to generate insights. The integration platforms, it centralized systems, example, the cloud dashboards, mobile apps that combine IoT data and AI analysis for crop growth prediction, pest and disease alerts, irrigation and fertilization planning. The data-driven techniques help boost agricultural productivity by increasing yields, reducing losses, and cutting down input costs. However, these techniques have seen sparse adoption owing to high cost of manual data collection and limited connectivity solutions. In this lesson, we present FarmBeats, an end-to-end IoT platform for agriculture that enables seamless data collection from various sensors, cameras, and drones. FarmBeats system, designed that explicitly accounts for weather-related power and internet outages, has enabled 6 months-long deployments in 2 US farms. An overview of the system is given in this figure. Here we discuss the main designs decision. How FarmBeats works. This is the system architecture. First, IoT devices. There are soil moisture sensors, weather stations, camera-equipped drones, tractors with GPS and embedded telemetry. Next is the edge computing gateway. FarmBeats uses an edge device. Example is the Raspberry Pi with AI capabilities that collects data from multiple sensors. Pre-process it locally to reduce bandwidth, then synchronize with the cloud only when needed. Next is the TV white space or TVWSS for connectivity. Leverages a unused TV spectrum to connect rural farms to the internet over long distances without cellular towers. On the other hand, the cloud storage plus AI models, so data, is uploaded to Azure Cloud. AI analyzes trends in soil conditions, weather forecasts, crop health, via drone images, pest or disease patterns. The visualization dashboards, wherein the farmers access insights via web dashboards, mobile apps, alerts, and recommendations. The core feature is that it has a low bandwidth connectivity. So TVWS enables rural connectivity where 4G or 5G isn't available. Edge AI processing, so it enables local computation even without internet. Soil intelligence uses ML to estimate soil moisture without sensors everywhere. And AI-powered imaging, drone or satellite imagery analyzed to detect crop stress. IoT can potentially be at the forefront of farming operations for sustainable agriculture. Significant advancements in wireless networks and 5G, fifth-generation smartphone communication technology can shape the upcoming internet technology, providing growers with important real-time updates anywhere. According to the business report, it is projected that by 2025, over 75 million internet-connected agricultural devices will be in operation. Additionally, it is projected by 2050, the average farm will generate 4.1 data points on daily basis. For the AI-powered predictive agriculture, next-gen models will integrate weather forecasts, market trends, satellite imagery, and historical data that predict yields, pest outbreaks, and market prices weeks or months ahead. Interoperable smart farming ecosystems. Cloud platforms will connect sensors, tractors, drones, and market systems in real time. Move toward farm-to-market data traceability and blockchain-based transparency. In conclusion, next-generation farming harnesses the synergy of AI, edge computing, computer vision, robotics, and IoT to revolutionize how we cultivate, monitor, and manage agriculture. These technologies lead to smarter resource use, higher yields, sustainable practices, and resilient food systems. As we look to the future, agriculture is no longer just about labor and land. It's about data, intelligence, and sustainability. With AI and smart technologies at the helm, we're cultivating not just crops, but more efficient, resilient, and connected world. The farms of tomorrow will be digital ecosystems, guided by insight, not instinct. Let us embrace this transformation where every seed planted is supported by science, and every harvest tells a story of innovation. That would be all, and thank you.